Our next speaker is Dylan Foster, who is a principal researcher in the RL group at Microsoft Research. And I believe you were formerly a postdoc at MIT, so he must be really good. His research focuses on the mathematical foundations of intelligent agents that learn from experience. And so I guess we have to get the, right now we're looking at the screensaver.
1 second.
Yeah. Okay, and so he's going to tell us about self-improvement with language models.
I'm learning how to put the microphone on from experience. Okay, let's see. Okay, it sounds like that's working. Great. Awesome. Yeah, thanks a lot for having me. Yeah, so this talk, kind of along the theme, right, is going to be about, right, how do we kind of equip like language models and foundation models with the ability to kind of like explore and self-improve on their own. To put this into context, I think it's helpful to look at kind of the standard language model training paradigm as it exists today. And you can kind of break this into 3 chunks. The first chunk is, what people call pre-training, where you fit a model to some huge unsupervised text corpus with next token prediction. The next stage is what's often called post-training or alignment, where you kind of fine-tune this base model that you get from pre-training to a task of interest, often using reinforcement learning. And then the last stage is what people call test time or inference time, where once you have this model, you maybe spend some additional time on the generation process to kind of improve the quality. And if you look at these 3 stages, pre-training traditionally requires, a huge amount of data and is very expensive, but this is where kind of the core capabilities of the model come from. Post-training is usually applied with much less data, traditionally for fine-tuning, and test time is kind of similar. We're going to focus on post-training, and the reason why I find this stage interesting compared to, say, pre-training kind of comes down to supervision. With pre-training, you're kind of explicitly supervising the model with examples of the behavior that you want, like, examples of reasonable-looking text from the internet. Whereas with pre-training, or post-training, I should say, if you use techniques based on reinforcement learning, you don't actually need to supervise with explicit examples of the behavior you want. Like instead, the process is, I design or I acquire some kind of reward signal that tells the model how good it's doing at the task. And then once you have this, you can kind of figure out which behaviors are good or bad through trial and error, right? So if you have seen any of these techniques like PPO, GRPO, DPO, these get thrown around a lot. These are all policy optimization techniques that, like, broadly speaking, follow this paradigm. Like, they treat the model as a policy to adopt the RL terminology. They use trial and error to optimize a reward. Okay? So what I said was, this is useful, this post-training paradigm, because it, you can use this even if you don't have explicit examples of the behavior that you want the model to do. Okay, but can this truly discover new behaviors on its own? That's kind of the question that I want to look at in this talk. And I think it's helpful to look at some examples of how people use reinforcement learning and how these stack up. So one we can look at is reinforcement learning from human feedback. This is where you kind of fit a reward model to human preference data, and then you use reinforcement learning to optimize this. This is not really for discovering new behaviors. It's more for tweaking behavior that's already in the model. Like, you kind of want to make the model, more helpful as a chat assistant or better at following instructions. Maybe a more interesting setup, which has gotten a lot of attention in the last year, is what's called reinforcement learning with verifiable rewards. The idea here is, if we think of domains like coding or formal math, here you have kind of objective feedback on whether you're doing a good job at the task, right? Like, if I'm trying to generate code with my model, I can just run the program it produces and see if it passes my unit tests. And so you can just use that as, direct feedback for reinforcement learning. This is like huge improvements in kind of reasoning capabilities in the last year. If you look at whether this is actually kind of eliciting really new reasoning behavior, the results here are actually a little mixed. So this is from a paper I like, which is called, Does RL Really Incentivize Reasoning Capacity Beyond the Base Model? And kind of what these results suggest is, rather than discovering truly new behavior, it's maybe better to think about current RL methods as just kind of amplifying or sharpening behavior that's already in the model, but maybe just had kind of low probability to begin with. Like you're taking, maybe my model has a 1 in 1,000 chance of generating the right answer when I prompt it, and I can like lift this up to, probability 1. Okay, but if I didn't already have kind of modest probability to begin with, maybe I'm out of luck. And that's all these plots are showing is, across a bunch of different tasks and different models, RL pushes up the kind of pass at 1, like the chance that the model gets it right on the first shot, but the kind of pass at n as you give the model more attempts never actually gets larger than what it was in the original model, okay? And, obviously I'm not trying to be dismissive here, like I really do view this as like a breakthrough, but just coming back to the kind of main question here, I do think it would be really interesting if we had a way to kind of reliably elicit new behaviors beyond what's kind of already in this model you get from pre-training. Just to say a little bit about why I think this is interesting, beyond like intellectual curiosity, I do think this is kind of like a necessary capability if you want to eventually arrive at kind of AI agents that can kind of solve open-ended problems and kind of self-improve on their own. And yeah, just from a practical perspective, I think if you don't have this capability, as you go to like longer and more complex like agent-like tasks, it's just going to be very difficult to get, explicit data that gives you like examples of the behavior that you want, right, as the horizon gets longer and longer, okay? So this is the high-level question. How might we hope to do this? If you've been following the RL literature, especially over the last decade, right, this is really just kind of the problem of exploration. Like exploration to me is really just asking, how do you incentivize your model to produce like diverse or, maybe more novel or informative responses so that it can learn from feedback as quickly as possible. If you go back to like the kind of Atari AlphaGo era of AI, there was a huge amount of research on this, like techniques for trying to do exploration with deep networks. I'm just giving like a few well-known examples here. All of these are kind of, heuristics for trying to take a policy parameterized by a deep neural network and get it to kind of like explore more novel responses. And these are all algorithms that are kind of designed to explore in new situations from scratch, just because there's not really like a base model in this setup. Like you're just kind of starting with like a randomly initialized network. I would say it's natural to imagine trying to adapt these techniques to work with language models, but yeah, like this hasn't really happened yet. I would say we don't have a good understanding of, like which of these techniques really scale or like how to scale them, or like what are the pitfalls that we should be aware of when doing this, starting from like a powerful base model. Like what do you need the base model to know how to do for this to work? Now to give a different perspective, exploration has also been like a huge focal point of reinforcement learning theory. This has actually been like the main thing in some sense that I've worked on in the last 5 years or so. And we actually do have a pretty, like, I would say beautiful understanding now of like abstract principles for like how should you do exploration with, like complex models. I guess if you're at the summer school last week, this is kind of what this tutorial Sasha Rocklin presented is based on. But the kind of challenge here is like a lot of the theory in RL, this was motivated again by this pre-sort of foundation model era, and so it doesn't immediately lead to kind of insights in how should you do exploration efficiently with like these very large models and what role the kind of base model that you get from pre-training should play. I think it would be really cool if theory could provide us some guidance in this, at least in terms of, maybe new interventions for exploration, but at the very least in terms of highlighting, are there like fundamental pitfalls or barriers that we should watch out for as we try to like develop better algorithms for exploration. And that's kind of going to bring me to the main sort of point of this talk, which is to give, an overview of some kind of new theoretical work we've been developing, in the last year or so that tries to, understand, when, if ever, can we hope to efficiently explore beyond our sort of base model? And what is the role of the base model in guiding kind of exploration and self-improvement? Like, in particular, what properties does it need to have for this to be possible, for sort of, open-ended exploration and self-improvement to be possible? Okay, so this is what I'm going to kind of, present in this talk, is some new theory that kind of tries to answer these questions, right, in anticipation of this maybe coming era of experience. Okay, so I'll start getting into results now. So to kind of set this all up formally, I need to give a little more detail into, how do we formalize this framework of post-training, where, again, we're starting from this powerful base model that comes from pre-training, and we want to adapt it to tasks of interest with reinforcement learning. So we need a couple definitions. First definition here is we're going to formalize a language model as a conditional distribution over responses y given a prompt x. Y here, right, we imagine as being like the full sequence of tokens the model produces when we prompt it. I'm not going to get into the details of like the auto-regressive sort of generation process at this stage in the talk. Okay, so for post-training, we start off with a base model that I'm going to call pi base, which we imagine, comes from pre-training or supervised fine-tuning. And what we want to do is fine-tune it with RL so that it has good performance on some task of interest with verifiable rewards, like math or code. So the formal learning process here is we have access to T prompts, which we'll call XT, that are just IID from some distribution. And for each prompt, we get to sample up to n responses and query our verifier for the reward with each response, right? And these responses, we could sample these from the base model. We could sample these from like iterates of some RL algorithm that we're running to update the policy as we're gathering more feedback. Okay, so our goal with this process at the end is to end up with a model or a policy, I'm going to kind of use these terms interchangeably, that has high reward. And concretely, I'm going to focus on what's called this KL, regularized reinforcement learning objective. So this just means we want to maximize the expected reward of our model minus the KL divergence from the base model. So this is like kind of the standard objective if you look at like post-training RLHF. The intuition is just, I want to maximize my reward, but I don't want to drift too far from like the initial model and end up with like crazy behaviors. This parameter beta, this is just controlling this trade-off, right? Like smaller beta means I can drift further away. This beta is going to come into the theoretical results I'm going to present. So this is going to make an appearance throughout the talk. Okay, so that's the basic setup. The last thing to mention is, when we talk about, what makes a post-training algorithm good or bad, there's kind of two different desiderata we can look at. One is data efficiency, which is just asking, like, how many prompts does the model algorithm need? How many times does it need to query this verifier or get a reward to learn a good model or policy? Second desiderata is just, what is the total compute used by the algorithm throughout the learning process? This is always at least as large as, the amount of data, just because, we need to, like, touch at least every data point at least once, right? So coming back to the kind of key question I sort of asked, right, like the main point of the talk, the reason why you might want to do something like exploration with language models is that ideally this should improve your data efficiency if the base model has poor support on, the behaviors that have high reward for your problem, right? Because you're kind of encouraging it to push up the probability on these behaviors with high reward. Ideally, you would hope that that should improve the just total compute used as well, just because, again, like, the amount of data you need is pretty hard lower bound on the amount of compute you need to use. Okay, so that's the hope. If you look at, what's actually known, though, it turns out that our understanding of, when exploration can actually improve data efficiency and compute efficiency for language models, this is pretty limited. And what I find useful to illustrate this is, I would say looking at probably the simplest class of models that we don't yet understand, which is what I'll call linear softmax models in this talk. This is kind of a toy setting where we assume that the reward we care about is linear in some kind of feature map phi of xy that maps the prompt and the response to a vector in r to the d. So just kind of an embedding of the response. So what you're assuming here is that the reward, this feature map is known to us, and the reward is linear in this feature map and some unknown parameter theta star. So when you make this assumption, you can show that the optimal model, like the model that maximizes the KL regularized reward, has this kind of linear softmax structure. I'm going to call this pi theta star, by the way. So it's proportional to the base model, but sort of tilted by the reward function. So tilted by this exponential in the reward, multiplied by the inverse of the regularization parameter. So I'm going to restrict kind of my attention to this type of model parameterization going forward. If you squint your eyes, this is kind of like a language model where you freeze all the weights except for the last layer. The reason why this one turns out to be kind of a useful toy model or a theoretical test bed is just that even though the embedding is low dimensional, this response space Y, can still be super, super large, like combinatorially large. So understanding this, like understanding how to get efficient algorithms in this setting, it's sort of a prerequisite for understanding like real language models where the response space, it's like the space of all sequences, right? So it's combinatorially large in the sequence length. Okay, and what I'll show now is, if we look at sort of standard policy optimization algorithms, so things like PPO, GRPO, DPO, if you've heard of these, all of these can kind of fail to explore beyond the base model, even in this linear softmax setting. The way we're going to quantify this is through something I'm going to call coverage. And this is kind of the main way that we're going to, formalize what does it mean for a base model to be good or bad in this talk. So formally here, the coverage coefficient, this is just the sort of worst case density ratio between the optimal KL regularized model in our framework and the base model that we're starting out with. The way you should interpret this is just, if this coverage parameter has, value C, then, in the worst case, I need to draw about C responses to a given prompt if I want to make sure that I see at least one that has high reward. So you imagine if the base model is very good, hopefully this C is kind of small. If the base model is not great, then, C could be pretty big, right? And this is obviously like a very kind of pessimistic definition. You can relax this notion of coverage and, kind of everything I'll say in this talk we'll go through, but this is maybe just the simplest to state, so we're going to work with that. Okay, but what I claim is, again, formally, in any of the sort of like RL algorithms that are used in practice right now can fail unless the amount of the data they collect scales either with this coverage coefficient or scales exponentially in the inverse of this sort of regularization parameter. So intuitively, this means you either need good coverage or you need like a trivially huge amount of regularization. So you're just saying like very, very, very close to the base model. And this is just reflecting the fact that, these are algorithms that are kind of passive. They don't have an explicit mechanism to incentivize exploration, right? So the data efficiency is not great here. The compute for these algorithms is actually decent in like a per round sense. Like at each iteration, you can kind of implement these efficiently, like provably efficiently in our toy model. But just because you need a huge amount of data, the total compute you need across the learning process is still huge. Okay, are there any techniques we can use that might, allow us to, explore a little more actively and do better? If you look at algorithms with provable guarantees for this toy setting, the main one I'm aware of is this algorithm we call exploratory preference optimization. This is from a paper we did about a year ago. The details of this one are not going to be super important for this talk, but the basic idea is just to kind of augment these policy optimization algorithms with kind of a bonus that encourages exploration. On the statistical side, this is an algorithm that can do much better than passive exploration. So the amount of data it needs is actually always just polynomial in your feature dimension and in the sort of accuracy that you want to learn the model to, irrespective of whether the base model has good coverage. So this shows, at least statistically, it is possible to explore beyond the base model in our toy setting. The fact that this scales with D is just reflecting that, there's kind of only D effective dimensions you care about in like feature space. But on the computational side, this algorithm's a little less satisfying, and it turns out that the training objective it requires is kind of like non-convex even in our simple toy linear softmax model setting. So it's not clear you can actually implement it efficiently when the space of responses is large. Okay, so is there any hope of doing better, like getting both the good data efficiency and computational efficiency? It turns out that unless we make more modeling assumptions, the answer is no. So this is a computational lower bound, and what it says is, in this sort of linear softmax framework, for a pretty general class of algorithms that just satisfy a certain kind of technical condition on how they access the features, the amount of runtime the algorithm needs does need to scale with this coverage coefficient in some kind of worst case sense. So this is kind of interesting. It says you do kind of need coverage, like you are kind of restricted to responses that are covered well by the base model, but for computational reasons rather than like for statistical reasons, which is maybe a little subtle. And the intuition here is just that, in high dimension, unless the number of sort of responses that you draw from your base model scales with this coverage parameter, you just might fail to discover like a single interesting direction in feature space that would help you explore. But are we out of luck? Like, are we really out of luck? Not exactly. So I would say the real interpretation of this is it's really a fundamental limit for what you might call like bandit style or outcome level algorithms that kind of only care about the final reward of the sequence you generate and don't have an explicit mechanism to kind of break the sequence down into chunks and figure out, if I generated a bad response, where did I go wrong? And so the main result I want to present now is that it is possible to do better and explore beyond the base model in this setting, but to do this, we will actually need to kind of dig into the autoregressive structure of the problem and, use algorithms that kind of break things down step by step. And this is going to kind of have three kind of key ingredients. The first is a new technique for exploration that we call spanner sampling. This is a kind of way of doing exploration that's optimally data efficient and uses as little compute as possible in light of the lower bound I was just showing. The second ingredient, this is the most important one, is we're going to use real kind of like multi-turn RL, so we will actually use kind of like dynamic programming techniques to break down the sequence and kind of think step by step. And it will actually turn out that for this to work, we will actually need to kind of increase the amount of test time computation that our algorithm uses for both of these parts. But the claim here is if we put all these three ingredients together, we will actually be able to explore beyond the base model and find new behaviors. And so let me just walk through kind of how we do this step by step. Okay, so let me start with this first technique here, this sort of exploration technique we call spanner sampling. The basic motivation for this is if you think about any of these algorithms I was describing as sort of passive like exploration, passive learning, all of these can be, like very wasteful in terms of the amount of data they use when the coverage is large, just because you might query your verifier with a lot of like redundant responses that don't really help learning. Like if I'm doing math, I might generate a bunch of responses that morally are using the exact same proof technique, but are using slightly different notation, or maybe organize things into like lemmas or different parts differently, but are still ultimately wrong for the same reasons. So the idea behind this algorithm is just to kind of be a little more deliberate and avoid querying your verifier in this redundant way. So concretely, what we do is, when we get a prompt, we're still gonna sample a bunch of responses from the base model, but we're not going to go and immediately query the verifier with all of them. Instead, we're going to try to like use the feature map to pare this down to a smaller kind of core set that only contains the responses we think will be like really informative, and then we just query the verifier just with these responses. Okay, and the data efficiency here will be much better because we're not wastefully querying the verifier. But just to sketch this formally in a little more detail, we're going to maintain this matrix I call sigma span. This is going to be like a D by D matrix. This is going to kind of capture directions that we've already explored in feature space. When we get a prompt, like if theta t is our current iterate, we're going to sample, we're going to sample up to n responses from this model. For each one, we're going to check if the corresponding feature map kind of has big norm under the inverse of this spanner matrix. If this is big, it kind of means we've discovered a new direction in feature space that we haven't explored, in which case we're going to query the verifier for a reward, add this to our data set, and update the spanner matrix. And if this isn't triggered, like if this doesn't happen, we just throw the response away. Okay. So this is something you can put in the loop of kind of any like policy optimization algorithm. Like ultimately, you're just going to update it as usual, but you only use the data that was collected with this process. So what does this get you in theory? Let me walk through the data efficiency and the computational efficiency. So in terms of data efficiency, we're doing pretty well in the sense that this is always polynomial in the dimension, the inverse of the regularization parameter, and the accuracy you want to learn to, irrespective of whether the model has good coverage. In terms of computational efficiency, this does scale with the coverage coefficient, but it's polynomial in this and everything else. And in some sense, this is like a best of both worlds result, where you're getting kind of the best data efficiency you could hope for, and yeah, your compute scales with the coverage coefficient, but this is kind of unavoidable because this is still kind of operating at the outcome level. Now, again, you still are paying the coverage coefficient here in runtime, which is not ideal. The reason this is useful is just that it's a building block for the next result I'm going to show you, which is that if we combine this technique with kind of dynamic programming, multi-turn RL, we'll be able to do much better. So the idea here is, for the results I presented so far, right, I was just treating the base model, or all of these models, as just abstract conditional distributions. What we're going to do now is, take advantage of the fact that these kind of explicitly factorize as a sequence of conditional distributions that I can sample from efficiently, right? Like, you can imagine that these YHs here are like tokens, right? This is the defining property of like autoregressive models. They give me a efficient conditional distribution over tokens that I can sample from. For what I'm going to show you, it's actually useful to think about this a little more abstractly and imagine that these YHs are maybe like chunks of tokens rather than individual tokens. This is kind of a modeling choice, and I'll explain how this comes in a second. I'm going to start calling these actions, though, but these can be tokens or big chunks of tokens. Okay, but what I'm going to do here is I'm going to try to use this structure to explore more efficiently, kind of viewing this as a Markov decision process where the state is just the prompt and all of the tokens we've generated so far. But to take advantage of this MDP, or this Markov decision process viewpoint, it's not enough to just use that the base model is autoregressive. I'm also going to assume that the optimal model now is what we call an autoregressive linear softmax. So this is just a generalization of the sort of linear softmax model I was showing before, where now the conditional distribution has this sort of, linear softmax structure rather than the full outcome level distribution, right? And there's a sense in which this is kind of equivalent to assuming that certain value functions associated with your MDP are linear. So you can view this as, it really is like the right kind of multi-turn analog of the linear softmax assumption. Okay, what does this buy us? In terms of sample complexity, not that much. The punchline will be that we can do much better in terms of the coverage assumption we need on the base model. And what we're going to be working with instead of the sort of sequence level coverage coefficient I was looking at before is what I call the action level coverage coefficient. This is very similar. It's just the density ratio between the optimal model's probability on a given like action, like a chunk of tokens, rather, divided by the base model's probability on the action. So it's just, instead of looking at the density ratio for the full sequence, we're just looking at the density ratio for the conditional distributions. This can be much smaller. Like even if this is 2 for every step h, the sequence level coverage, can be as large as 2 to the sequence length, just because you're kind of going on a random walk. Okay, so this is the punchline. If we use this kind of multi-turn version of this spanner sampling algorithm, where we do sort of, dynamic programming, but we interleave this with this spanner-based exploration over actions, we can get data efficiency, which is, still polynomial in all of the problem parameters, but now our runtime for the algorithm only scales with the action level coverage rather than the sequence level coverage. So what this means, right, is, even if your base model has terrible coverage over, the behaviors that you care about and that you would like to elicit at the sequence level, as long as it has good coverage over like individual chunks of sort of the behavior you want, like maybe individual like lemmas in a proof, you can kind of stitch these together to get novel behavior that you would be very unlikely to find with just naive vanilla sampling from the base model. Okay, so this is like a very stylized result, obviously. Like, all this is very specialized to like linear models, but I do find this pretty cool as like a proof of concept. It's showing, right, there is hope of discovering novel behavior beyond the base model, and using this to self-improve if we explore deliberately. There's still obviously a huge amount to be done in terms of understanding, like, can you actually like scale these sorts of techniques? Along those lines, we'll give maybe a teaser for some ongoing kind of like empirical work. So this is just a plot where we've kind of been investigating, exploration techniques based on this spanner idea for reasoning problems. So what this is showing is 2 different algorithms for kind of test time sampling and comparing like how many verifier queries do they need to find like a response with high quality. So one of these lines here, which is just vanilla sampling from your base model, this is the blue one, and the orange line is kind of an algorithm inspired by this spanner sampling I showed, where you generate a bunch of responses, but you pare them down to a small set that you use to query the verifier. And this is actually just using the last layer hidden features on some pre-trained base model. So it's just kind of pretending that we're in this linear softmax setting and just seeing what happens. But what we see here is, for this coding task MBPP with this Quen base model, we do actually get a pretty substantial improvement in, the amount of data you need for like the hardest quantile of problems. So in some cases, it can be up to like 10 times smaller. Here's another similar plot for math rather than coding, where we see kind of a similar benefit. And it seems like this persists across, like a bunch of different, choices of base model and kind of like reasoning tasks, like math, GSM8K, MBPP, AMY, with the caveat that, for very weak models like this 0.5B Quen model, you don't see a whole lot of lift. But I find this exciting. It's kind of cool that you can already see this improvement, even though this is a purely like test time algorithm, so we're not even doing any like updates to the model yet. And even though we're just using like the model's frozen features, which like a priori should not satisfy all the assumptions that the theory requires, right? So hopefully we'll have some more results along these lines to show you all soon. I'm getting pretty close to the end, so I'm going to start wrapping up. I think in the interest of time, I'll skip this result and just say the TLDR is, this spanner sampling algorithm, it uses extra test time compute, right? Because when you get a prompt, you generate lots and lots of responses, but you ultimately pare them down to a small set that you use. We have a computational lower bound which says there's a formal sense in which you probably need to use like a certain amount of test time compute in order to get the style of guarantee that the algorithm achieves. But you can check out the paper for more details on this. I'll just wrap up. So again, the main message here is there is hope of efficiently exploring beyond the base model with language models and foundation models. But to do this, it seems like we really need to dig into the structure of the problem more and start thinking about, how do you explore deliberately? How do you do multi-turn RL and break the problem down step by step? There's obviously a huge amount to understand here. Like on the theory side, if we go beyond this sort of linear setting, we've really barely scratched the surface, and I think that's a fascinating problem. But yeah, I'm pretty excited right now about just, playing around with these things empirically and getting kind of signal on, which of these modeling assumptions and interventions actually work and which ones do not. The last thing I'll mention is just, this is kind of part of some broader line of work we've been thinking about around, foundations of language model post-training, let's say, and friends, which I view as kind of just updating like learning theory and reinforcement learning theory to, just better address this era we're in where, we want to design interactive decision-making agents, but we're starting from this powerful pre-trained base model. So how do we really like take advantage of this? How do the principles and like what the interventions look like change? These are some other works from our group if you're interested in this, but I'll also just direct you to check out Akshay Krishnamurthy's talk on Friday in the workshop, which is also covering some of our work in this direction. So maybe I'll leave it there, All
right, thank you. All right, we have some time for questions right here.
Thanks very much.
For sure.
About the spanner sampling. Is there anything special about the spanner construction in kind of two senses? I think you're trying to push the features off the kind of the base model distribution in order to have sort of a wider set of sampling. Is the spanner construction important about this, or are you just trying to get off the base distribution?
No, the specific construction like is important. It's kind of related to actually like optimal experimental design. If you go back into that kind of like classic like statsy line of research, you're just trying to get a collection of features that's as small as possible, but just sort of like maximally spans every direction in feature space. The only difference here is in sort of classical settings where you imagine maybe the space of responses is not too large, you can kind of hope to achieve this property in like a uniform sense. Here, because it's very large and all we can really do to hope to like explore this is sample from the model. So you have to settle for a little bit more of like an average case version on the theory side, where it doesn't cover every direction perfectly, but it covers them as much as you need to for like the downstream algorithms to work. Mm-hmm.
And is that threshold that you apply in order to accept a sample, is that progressively getting harder, or does that stay where it is?
That's a good question. You could say that progressively gets harder. In the sense that the sort of like optimal threshold, like, okay, if you in practice this would be like a hyperparameter, but if you go and like actually do the theory and like optimize, your like sample complexity and stuff, it needs to scale with like the sort of like final accuracy of the model that you're hoping to learn. So
Is it me? Okay, sorry. Up here. Yeah, that was a lovely talk. Thank you very much. I'm a physicist, and my reinforcement learning expertise comes from applying it to physics problems, definitely in the pre-base model era. It seems like you said a number of things sort of explicitly and implicitly about credit assignment. There was your theorem that assumed no credit assignment, and sort of implicit in what you were saying is that there's some precise assumption that is correlated with it. And then later on you're talking about stitching together actions, which is sort of saying that this set of actions in sequence is responsible for getting credit for the problem. How do I sort of generally think about this in the space model era? Credit assignment, what has changed, et cetera?
I would say in terms of like what has changed in the base model era, right? It's like, credit assignment and everything still makes sense. It's more that, I would say in some sense the main message is you have this additional kind of like computational tool, which is like the base model. So you can kind of use this to maybe like, do credit assignment over like a larger space than might have been tractable previously if you were just starting entirely from scratch. If you're going to go and do like value function approximation in so if you want to go and do like reinforcement learning with deep models, right? Like the basic principle of like dynamic programming makes sense, right? Like it's still just like I try to fit a value function and use this to like guide the actions that I select. But how do you actually do this when you're starting from scratch? It's like very easy to get stuck, right? And kind of what having a base model is allowing you to do is, do a better job at like not getting stuck, right? Or if you do get stuck, it's ultimately still like you were starting from a better place to begin with. So like you're
Thanks.
But yeah, you can check out the paper if you want to kind of see in a little more detail formally like what all these definitions actually mean. Yeah.
Thank you.
Yeah.
Yeah, thanks for the nice talk. I had a question about the kind of basics setup in these kind of post-training setups. So like the reward function, what does it look like? So let's say you have like a bunch of math problems and so on. So do you reward only at the very end to find an answer, or do you do like some step-by-step rewards, like to find the right approach? And
yeah, good question.
Like how do you formulate it? And I mean, also if it like generates some prompt, I mean, like that step might appear at different points. So how do you how do you figure out how to structure the reward?
Yeah, so for the reward, in terms of how people actually set this up today, it is just at the like outcome level. Like literally, it is just I give you a reward if you like follow the formatting instructions and produce a program that like runs and passes like 10 unit tests that I've like specified. So like this sort of thing. Or for simpler math problems like, like grade school math, it's literally just like there's a numeric answer and you either produced it correctly or you didn't.
So do you use some kind of structured generation for this to ensure that it kind of outputs some kind of machine readable thing, or it just fails to reward if it just...
You just fail to reward if it doesn't. But like the base models are kind of strong enough that they can do something reasonable looking if you tell them to,
Okay.
But to answer your question about like intermediate rewards, for the final result I was presenting, you are sort of, you're learning what's called a value function, which is something that gives you a sense for what is the reward to go if I'm at like an intermediate step. But that's not something that you sort of specify as part of like the task itself. It's something that you are learning as a tool,
Thanks, Dylan. Great talk. So when you talk about doing this kind of sampling procedure for exploration, it sounds like you're still treating the problem as a bandit. Do you think that there is improvement that can be made from, treating this at a per token or thought or whatever level, where you're actually like performing search? And,
so that's actually kind of what I went through it like pretty quickly and like didn't give any details on what the algorithm actually looks like. But that is like morally what this one is doing. So this is actually doing spanning, like it's doing the spanners kind of at the like token or like chunk of token level rather than at the bandit level. So it is much closer to search.
Okay, very cool. Thank you.
And it does. So it does make a difference on the theory. Yeah.
So you talked a lot about using the RL to fine-tune the models and do better.
Yeah.
Can you go the other way and just use it to figure out where the base model has lacks of knowledge and just really needs to go back and have some data added to the pre-training?
That's a really interesting question. I mean, you could imagine, right, like when we talk about doing exploration, this really is just about like how do you automatically curate like high-quality data or useful data, right? So you could absolutely imagine going and like taking the data that these prompt response pairs that these sorts of like algorithms find and go and use them to pre-train. Yeah, it's a totally reasonable thing to do. And in some sense, like people are already doing that in practice right now, right? Where like people will go and like train a huge model with reinforcement learning, but then just, like it knows how to do, like grade school math now. I can go and then generate a bunch of reasonable looking like traces of grade school math problems and then just go and use those to train a smaller model directly. Yeah.
Okay.
Yeah.
Yeah, it makes sense. All right. Any last questions for Dylan? Okay, if not, let's thank him for excellent talk.
Thanks a lot.